Yeah, so I've been doing Elixir now for about 3 years, and 2 years ago I got into a project that this talk is based on. A lot of the outcomes as far as building a data processing platform to handle lots of data, and the cornerstone was the ability to handle connected vehicle data, and I'll go into why and why that's a big issue for us. So to give you a little context, in 2016, city of Columbus, Ohio, where I'm from, won a federal transportation grant to make Columbus smart. And what that meant was to gather lots and lots of data from all over the city. Cities produce a lot of data, and right now nobody really knows what to do with it or even where to find it. So we wanted to collect it all from all the different sources. A lot of those sources are really dirty CSV files that some city employee or business owner entered in an access table somewhere, be able to clean it, normalize it, and make it actionable, and then make it presentable back to users anywhere in the city so that they could do stuff with it, do valuable things, and from the federal DOT's perspective, improve things like safety and efficiency in the transportation system of a smart city. So we got involved with the project, which birthed the SmartColumbus operating system. It was a subset of this grant program that we won, and the idea was, again, to collect all that data and use it and be able to present it back to folks to make valuable use of it in this new, connected, very data-rich world. And about a month ago, several of us rolled off the project. It's starting to wind down. It's in that sort of reporting phase at the end of a grant life cycle when they're sort of just giving the results back to the DOT to justify that the money was spent well. And we took a lot of stock of what we did and how we did it. We did everything in Elixir. We did everything, well, all of our custom code was done in Elixir. We did it cloud native architecture out of the box, did it all in microservices. But we realized we made a lot of early mistakes, things we didn't plan for ahead of time, things that we wish we had known going into the project, even with several of us having built data platforms multiple times in our careers previously. And we kept saying, in hindsight, we would have done this thing differently. So then the three of us came together and we built Hindsight, which is the version 2 of this thing. And it incorporates all of the best practices and principles that we came up with having gone through the first iteration of this project. Again, it's all in Elixir. It's making a lot of use of a lot of the high performance data structures and protocols and all of the best things that we gained from our experience previously. So one of the principles going into the original SmartColumbus OS, and certainly now in Hindsight as well, was there were sort of 3 guiding principles. One was scalability, because we wanted cities of any size, something as big as Los Angeles or something as small as, say, Dublin, Ohio, which is a suburb of Columbus, to be able to run this thing and only consume and pay for the resources that they needed to use based on the size of their data and the number of interactions they were going to have with it. Another one was composability. So if we want to allow a city or a company to adopt this project, maybe they don't need all of the microservice components that we built. They need some of them, and they want to make the whole process as fast and efficient as possible, and again, streamline for cost by cutting out some of the steps that they don't have any use for. So we did it in microservices. We built it all in Kubernetes as a result of that. But the final thing that we wanted to differentiate ourselves from other products that might try to accomplish the same tasks, there was a lot of research early on into how big was Hadoop going to be factoring into a platform like this. The original assumption was a lot, but as we got further and further and learning a lot about the restrictions and the constraints that the various aspects and concerns for the project had, we realized we had to do a lot more heavy lifting on our own custom development using Elixir. So what we wanted to do to differentiate ourselves from those other platforms was streaming data. That was going to be where the magic was, right? We were going to handle that gracefully, much better than anybody else could and much more easily, right? Like, you can do a lot of this stuff in something like a Spark job, but it's really hard to work with Spark and Hadoop, and we didn't want to make users have to adopt that kind of thing. So an early proof of concept that we put before the city was, can we do real-time streaming data? Yes. And so we put together an application that used, at the time, a very minimal skeleton of what we grew the project into, that took data from the local transit authority, CODA, took data from the bus fleet, real-time data that the bus fleet was generating, sending back to CODA, and we displayed those buses on a map. We called the application Buses on a Map, You can see the little drop-down window there. You can filter based on the route you're interested in, and the buses are going to update in real time based on the data we're getting, the directionality that we're getting. This is all coming over a standard that Google developed called GTFS. It comes in a protobuf form. We read that in, we ingest it, and we stream it out of Phoenix WebSocket. And then this React application on the front end is presenting that to the user and making it actionable. So again, we are processing data as fast as we can, as fast as we're getting it. But one of the things that we learned when we're talking in particular to cities is different people from different perspectives have a different idea about what does real-time mean. And it turns out if you are not in computing, and in particular in cutting-edge computational field, real-time can mean roughly every 10 seconds, which is how frequently the buses were generating their positional data. So that's a very different opinion on what real-time means, but we're still able to present it in as real-time as we're getting it. So we figure we're ready to handle real-time data. We're ready to handle a lot of it. So we're going to dive right in and start consuming that data as fast as we possibly can and make it usable to users. So again, our goals are to ingest a lot of data from a lot of different sources. We're going to stream it through a pipeline. We can do arbitrary transformations on it. We can value add by doing things that might be useful. We can clean it up, and then we load it. And when we consider load, it's a two-pronged approach of we stream it back out, we broadcast it over sockets so that applications could hang off of the back end of this ingestion pipeline and make the data usable to users in real time. But we also persist it into a long-term storage so that researchers or city employees can query the data and join it and do things to gather valuable insights over time. So the gold standard for being able to handle true real-time data at volume, like the last slide was implying, was the connected vehicle environment that was going to be coming online as a part of the broader SmartColumbus project. And so what that means, it boils down to, and the image here is sort of outlining this, is connected vehicle environments. There's a couple of standards that are still competing. This is sort of the Betamax VHS war all over again. But one of the standards that was going into this particular deployment was based on something called DSRC, or I believe distributed short-range communication. And so there's a radio frequency that's not, I believe it's between Bluetooth and 802.11. And the idea is that vehicles and roadside infrastructure and even like devices that people are wearing on their person, they're in an environment all talking to each other. And they're all sending messages back and forth in high volumes, in short increments, to tell the environment stuff about where they are and what they're doing, where they're going, and the state of the device or the vehicle. So like transaction, like a vehicle's braking system would be one aspect of one type of message that a vehicle in a DSRC environment is sending back and forth with the environment. And then those roadside units, or RSUs, they're collecting that stuff and they're broadcasting it back to some sort of controller unit. So one of those was going to be going into Columbus. It was going to factor in about between 1,500 and 1,800 vehicles, a combination of public and private fleet. We're going to be outfitted with these devices, about 200 roadside units, and this was all going to be spread along a corridor with roughly 17 of Columbus's most high accident-prone intersections. And this was all going to be due by June 2020. We started working on the back end of this project to consume and collect all this data in October. So to give you an idea of what this looks like, in Columbus, a suburb of Columbus called Marysville has a Honda plant. And because of that relationship, they have an intersection in the middle of town, the two biggest streets that cross, has a small collection of maybe a half a dozen RSUs, DSRC deployment. I believe all of the company-owned and employee-owned vehicles have the DSRC modules installed in them, so they're all talking back and forth. So we had access to a sample data feed to be able to start testing against. And to give you an example, so we got a Docker container that hooks into that network, and it publishes to an arbitrary endpoint. The endpoint was going to be our application, our pipeline. And so I'll give you a quick visual, I'm not going to try to do this live, of running this thing, and you can see what it looks like generating that data. Now this is from a single intersection, roughly about the middle of the day. That's a lot of data coming very, very quickly from maybe a half a dozen vehicles at any moment. that as they enter and exit this ecosystem. So going and getting the data, like we were doing with the CodaBuses, is no longer an option. So we have to catch it. We're going to accept pushed data now. We're going to build a push gateway. We're going to be able to have them send us the data when and if it's ready to come to us. So how do we do that? How do we do that? Well, one of the easiest ways to do it was going low level. So hitting GenTCP and GenUDP built right into Erlang. The messages that you saw were coming over UDP packets. So we're going to be able to handle that with a very simple low level libraries that come to us out of the box. But then we try to backpressure a little bit by wrapping a gen stage around that. So if we turn this into a gen stage pipeline, we can backpressure into the UDP socket and as messages, because one of the features of GenTCP and GenUDP is the ability to set the socket to active or passive. And if it's in active mode, it is receiving packets, receiving messages, and sending them along their way. And one of the ways you can do that is you can set it to an integer and say it will decrement automatically as it receives messages on that socket until it reaches 0, and then it transitions into passive mode where it's no longer working, or it's just in sort of a wait mode to transition back into active. And by using GenStage to send batches of messages, we can then send a signal back to the parent socket to say, I have now capacity to handle n numbers of messages again, reset that counter so we can keep counting down. So effectively, we are always in active mode as long as we are handling messages, but we have the backup to say a circuit breaker and hold off if the system gets overloaded. So the question then becomes, do we ingest this data immediately? Do we send it directly into our backend system and publish it and persist it? Or do we do stuff with it in batches? Do we process it in real time within that process or within the application that has that GenStage pipeline built into it? And this became a question depending on the use case, right? Like if we have an application that wants to consume this real-time vehicle data and be able to do stuff like, say, present a HUD in a user's vehicle that gives you feedback information based on the environment and all the other vehicles in it, we need to trim as many microseconds off of that ingestion pipeline as possible. So we're going to try to cut network hops within our own system down and immediately send that back out that broadcast socket. And that means we need to have the flexibility to say, within this application, this push gateway, we want to do arbitrary transformations and manipulate the data as needed before we send it out. And that way we can send it out right away if we want to. So I did a proof of concept library that is cutting off the screen. So the joke is not entirely there. But this library is out on GitHub as a proof of concept called Salt and Pepper because we're building a push gateway and it pushes it real good. But I kept going and saying, like, if we want the flexibility to be able to do stuff to this data within that application, so we eliminate some of those network hops and we can get down to that sort of microsecond interactions, present it right back to the user as quickly as possible, we need to do stuff in the application. We can't send that over the network within our own platform to do those in subsequent microservices. So building out the ability, so we have our push gateway at the front there, and we have a processor to do arbitrary transformations or computations on it. We've got a reducer as an option, right? Because say, vehicles sitting at an intersection are generating, tens to 20 messages per minute. And a lot of that is, I'm still here, I haven't changed, and that's a lot of duplicate data that's not really useful to us. We want to be able to weed out some of that duplicated messages. And then we have a dispatcher at the end of the end consumer of this GenStage pipeline to send it along its way. And so over here on the right, you see the configuration for an application built using Salt and Pepper. And does that look familiar to anybody? Well, a friend of mine on the project pointed out it really looks like you've just re-implemented Broadway. And I am not nearly as smart as the folks at Plataforma Tech, so it wasn't going to be as good as Broadway. So if this becomes anything more than a proof of concept in the future, we're probably looking at turning it into a Broadway producer library to hook into Broadway and be able to take advantage of all of that safety and redundancy and still be able to scale or parallelize the processing of those stages the way that Broadway lets you do. And I'll get into some more Broadway in a minute. So some lessons from the receiving end of our it's good. So some lessons. Keep it simple, right? Go as low level as possible, as few interactions as you need to, and use what you've got built in if you can, because a lot of times you can get pretty far with that. And again, you want to keep these interactions as quick and as minimal as possible to get data through the system as fast as you need to. Another one is don't be afraid of Erlang. And I know Todd, I believe, is going to go deeper into that later today. But there's a lot of gold there, and you should be looking to it when you need to. So now we've got data in this system. We need to parse and decode it, right? So we've got compressed messages in raw binary coming in. Those messages you saw flying across the screen, that was raw binary as the payload field within the JSON that was sort of the wrapper of that UDP packet. But Erlang and Elixir give us pattern matching against raw binaries, which is, you're not going to find a better ecosystem to do that than Erlang and Elixir. So let me give you a look at some code that does.
It's not a signal loss thing, it's projected because I'm getting the signal back here.
OK. So it gives you the ability to this is what I do when I have to read raw binary pattern matching Erlang code too, as I fritz out. If it comes back online, you will see some Erlang code that actually parses the packets of raw binary and turns them into maps, map constructs. But that's really hard to read, and it's even harder to write. So the good news is that Erlang comes with a library called ASN1CT. And ASN1CT is a compiler for ASN1, or Abstract Syntax Notation. It's a sort of language-agnostic tool for defining data structures that can then be compiled into language-native data structures for any language that implements a compiler to do that. And again, Erlang comes with one out of the box. There are a number of libraries out on Hex to hook into ASN1CT in an Elixir application. And so I used one of those to generate the code that you saw before. But again, it's a raw map. And there's only so much you can do with that. And if you need to assert on, say, the quality of the data, or you need to be able to do stuff with it, you need to be able to put that into a more performant data structure. And so we have structs, and then we have protocols to be able to perform common operations on those structs that we might need to do across different message types. Because one of the things about DSRC is that the messages are, there are a lot of different types of messages, all with very unique structures to communicate certain aspects of interactions within that environment. So I wrote another library around the ASN1 auto-generated code called Kit for talking to a smart car. And what that does is it creates Elixir structs around these messages and with well-defined types, and then we can enforce certain behaviors and protocols on those things, like, say, now we've translated this into a human-readable and actionable data structure, and then we can serialize it into something like JSON so that we can send it down the pipeline and have it be easily acted upon later on. So now here's an example of running that application, that data feed. In the background here, you'll see that that Docker container that's publishing to my localhost is still actively running, and I'm going to fire up an application that has Kit built into it to do the parsing and decoding, and then pushes it through that push gateway. So I'm going to just open up the IAX session. I have the data feed publishing in the background, and in a moment you'll see messages start to fly across the screen in batches defined based on the configuration I popped up a moment ago. And if it comes back online, you will see that I have done an arbitrary transformation. I've decoded those messages into human-readable formats. I've pulled out some of the fields that I care about, and then I'm batching them as I send them on the way. So some lessons we learned about the decoding and the parsing is the power of binary pattern matching is pretty much unmatched in this ecosystem. And also, when in doubt, again, check OTP. There's probably something in there that you can use and that will save you a lot of headache later on. So the next thing is Kafka. We are inside of a microservice architecture. We want this thing to be composable so that different users can adopt only the pieces that are useful to them, or they can even insert other pieces that might be useful to them later on that we haven't envisioned yet. Kafka was the way to do this for a number of reasons. The main reason was raw throughput, because Kafka is going to beat pretty much every other message queue out there as far as raw throughput, under the circumstances, at least, that we were facing. So to give you a quick benchmark, a single Kafka topic optimized by multiple partitions, can process about 100,000 messages per second, where compared to RabbitMQ, which tops out at about 20,000 messages per second. Now, Rabbit has additional features and is more useful in certain cases. For instance, Rabbit can have as many queues, I think, as you could possibly want, whereas Kafka does have an upper bound on the number of topics and partitions it can support before it starts to have degradation of performance. But for our use cases, we wanted to use Kafka for that powerful raw throughput. But we needed to be able to do that in a way that the Elixir community ecosystem didn't really support at the moment. And so we built ELSA. So ELSA is a library that wraps the broad Kafka interactive client. And what it does two things. It allows us to handle interactions with Kafka much more dynamically than broad allows you to do. And it also sort of takes some of the control back from the supervision strategy that broad enforces on you. So it allows you to be much more dynamic and say, like, we want to use these features of Kafka, but we're going to lose out on performance if we start to have too many topics. And the way we've architected the system, every data set gets its own topic to be able to parallelize and not degrade the performance of any one data set as it passes through the system. And to do that safely, so we don't lose performance over time, we need to be able to do stuff like allocate and deallocate topics on the fly. So ELSA lets us do that, but ELSA is still only consuming from a topic, say, in serial. So we need to hook into Broadway. And so what Broadway did, Broadway was the perfect solution, but at the time we started to look at this, it was still relatively new and it didn't have any interactions with Kafka. We actually talked with some of the team at Plataforma Tech. We got some feedback from them. They were already starting to look into Kafka, but having done this type of work in the past, we had a lot more experience with Kafka. And so I think we gave them some feedback on their official Broadway Kafka library. It's, as I recall, it's not out on Hex yet, but it is out on Dashbit's GitHub if you have interest in looking at that as well. But one of the things that off-Broadway Kafka does that, to my knowledge, Broadway Kafka does not, is that it gives you two operating modes, one of which is sort of the classic mode that you're used to if you've ever hooked into Broadway as a producer before, and that's, Broadway, we spin up a Broadway pipeline that starts up an ELSA client, and then it consumes for that topic, one Broadway pipeline per topic and one ELSA client to do that for us. But we also have what I called the Showtime mode, which is another little Broadway pun, that inverts that strategy where we have a single ELSA client that we stand up to interact with a topic, and the topic gets read to see how many partitions it has, and then it goes out and it creates a Broadway pipeline for every partition on that topic. And then within those, you can have an arbitrary number of Broadway stages. So you can massively parallelize using Showtime mode. And we're really flying now as far as the amount of data that we can process through the system and apply those transformations or do other things to make that data as valuable as possible. So some lessons we learned there: parallelize everything, everywhere you can, as many times as you can, because you're really going to realize the true value of working in this ecosystem when you can take advantage of the concurrency that it gives you. And another one that we learned was processes are cheap. You should use lots of them. If you look at the supervision strategy for ELSA, it's fairly complicated, and we keep throwing processes at it to make it more reliable and more redundant and more resilient. But it really doesn't affect performance because of the way the Beam handles processes and how cheap they are to run. So then finally we've got the load stage. And again, loading in our case is both broadcasting out on a Phoenix WebSocket to a consuming application, but also it's persisting that to a data store. And in our case, a data store is an object store, so think S3. Because we're talking about a volume of data that is theoretically unbounded, we haven't really defined with users and potential users what the life cycle or what the lifetime of this needs to be. So we want to be able to grow this infinitely, as much as you can, as long as you can pay for the storage. And you're not going to get a better price for the volume of storage you can get than a cloud provider's object store like S3. So to do that, we use a tool called Presto. And if you're familiar with Hive and Hadoop, Presto is sort of the next generation of that sort of ecosystem where instead of an HDFS file system distributed across a cluster of compute nodes, we've got a SQL query engine layered on top of that cloud-based object storage. But the problem with that we found was that everything is still running through Presto's coordinator. So Presto is a Java application, and it has this strategy of having a single coordinator, and it farms, that takes queries and it farms the work out to worker processes and then returns those through the coordinator. And that worked great to a point, but for instance, we had one particular data set, it's historical data, so it came in a CSV file, but it came from a vehicle data company called Inrix. This was about 350 million records from a single year of vehicle data within Columbus. And exclusively because of having to back up the system as it SQL queried batches of these records into Presto, it took about 4 weeks to ingest all that data. And it was flying through the system until it reached the insert stage. And because it was, we would consume the entire file within half an hour, let's say, but because there was so much data backed up after that at the insert, it would flood Kafka's disk and crash the system. So we actually had to break up that file into 10 smaller files and ingest over a period of 4 weeks. So we asked the Kafka, or the Presto coordinator, what is it you do here? You're not really providing a lot of value on the insert side. Now queries are a different monstrosity. And we continue to use the Presto for querying the data out today. But we wanted to be able to avoid having to write through it for that performance gain alone, but also because a single coordinator is shared for writes and reads, we wanted the users and the front-end application that actually queries that data via Presto to not have to wait for writes to do reads. So we looked at the way that Presto works, and if you look at that, what Presto does is it maps a table definition, a schema, over files distributed across this file system. So as long as we write a file in the form that we are expected to read it, we use Presto to create that table, define what the table is, the columns it's going to have, the types of data that we expect to be in those columns. We just put the file on the file system, and it reads it like it had written it there itself. And we can do that in any number of these highly optimized formats for storage. We've chosen Avro now because of the sweet spot of it's more compressed, saves more space than JSON, but it's much easier to work with in Erlang and Elixir than Orc. Orc is pretty painful to work in unless you're writing in Java, because there's only one official Java client. But Erlang has a library built in, I'm sorry, not built in, but it has a library with great support for writing Avro files. So by a combination of Erl Avro and EX AWS, our persistence application, our persistence microservices, take the data off of the Kafka topic, and it appends that to an Avro file. And after a batch, I think default to a megabyte of data, maybe, or a certain timeout has passed without receiving data, we write that file directly into the AWS file system on S3, and then we wait for the next message to come in. So some lessons there is sometimes when you want something done right, you probably have to do it yourself. And use the right tool for the right job. So to get us off the ground, to prove out the feasibility of the system, Presto was great for writing, but it was too slow, and we really needed the performance, so we went to the right tool, which in this case was Avro. And to give you some idea about performance, to wrap this up, so about a week ago, we were writing about 100,000 messages fully ingested in hindsight. So from the front end, from the producer that sends it into the system, to the persistence layer, the WebSocket broadcast takes no time at all. So the thing that was really still taking a lot of time was writing it into Presto and then being able to query it out to validate that it got there safely. That was between 48 seconds and a minute, 10 seconds. Now, to give you some more numbers, that's a single partition on those Kafka topics. That's 2 topics. One from the ingestion phase, between that and the transformer, and then from the transformer to the loader. That's one arbitrary transformation. So we're not just passing it through the system. We're taking every single message as it passes through the system, and we're renaming a field on it. And that's only with 100 Broadway stages. And we could continue to parallelize that by expanding that number. And that was using the Presto SQL insert method. And we figured that was probably going to be our biggest bottleneck. So we finished proving out the Avro write directly to the file system. And now our time goes to 16 seconds for those 100,000 messages. Now, to give you an idea about what that actually amounts to in terms of that Inrix file with 350 million records that took 4 weeks to do, that's 500 million messages per day, per data set. Because we can parallelize across topics, however many topics of data that you need to go into the system across whatever domains you're consuming data from, we can parallelize, and the only thing we need to do is scale up the compute as we start to reach the bounds that we've put on the system. And because we've done it in Kubernetes, we can do that very easily. So I think we're in flavor country now. We're moving pretty fast. And that's all I've got. Thank you very much. Feel free to reach out to me if you have any other questions. I'm on Elixir Slack and Hex under that username. If you're interested in any of the code, the 3 main contributors are myself and Brian Balzer and Johnson Denon. The Smart Cities data, the original version 1 is out there on GitHub as well, that organization. And then our version 2 is in hindsight, sort of the spiritual fork to Smart Cities data. Those are all available. It's open source. It's a federally funded project. So all of that stuff is your tax dollars at work, and you should benefit from it as much as anyone in Columbus does. Thank you.